So this is forces and motion 2. Okay, there are 4 main subtopics in this one. So uh, there's the resultant force, there's the resolution of forces, then there's forces in equilibrium, and finally Hooke's law, which is like way out there lah. Okay, but of the 4, it's interesting that this particular module has all 4 subtopics covered. So I hope that whatever that you learn, okay, you can get a little bit out of every subtopic now. Okay, let's begin now. So the Penang first question is diagram 2.1, 2.2 show a lawnmower moving with 2 different methods. One is with a pushing method. Okay, the second one is with a pulling method. Okay, and we find that the force F, okay, over here can be resolved into vertical component Fy and Fx. So your first job is to make sure that if you see a directional like this, you need to know how to resolve it. Okay, resolving means you break this particular direction, okay, into 2 components. And when we talk about 2 components, it's either up and down or it's left and right. So when you look at this direction of the arrow, you know that it's going down and right. So one force will be downwards like this, and one force will be rightwards like this. Okay, this is what we call the resultant force. Okay, if let's say the 2 blue forces that you see over here, oh man, hold on. Okay, if you see the 2 blue forces that are over here, when you combine them together, it results in this force. Okay, that's what this means. So the flip side of it, if I give you a resultant force, you must be able to tell me what the resolution, what the resolved forces are. Okay, the resolution of forces lah. Kalau dalam bahasa Melayu bahkan it's called leraian. Okay, kamu leraikan itu daya kepada 2 komponen sama ada atas bawah dan kiri kanan. Kiri atau kanan lah. So likewise, with this one, you will also see the same pattern. It's going this way, okay? Therefore, one must be going up and the other force must be going right. Oh no, sorry, this is not right. Okay, but the idea is there lah. Okay, so the basic idea behind resolution of forces, okay, is if I give you a slanted force, a salient force, you must be able to tell me what the two components are that make up this force. So our first question is, what is the resolution of forces? Okay, so the resolution of forces is the process of the word resolving. Okay, and I like this word because it's very close to our key concept. Okay, process of resolving a force into 2 components. Okay, horizontal and vertical. Okay, so you break the force into the horizontal component and the vertical component. Okay, so that's what calls it the resolution of forces. So of course, our main job is to make sure that we know how to draw the resolution of forces. Okay, so draw diagrams of triangle to show the resolution of forces in this one. Now, we have to take these 3 forces, okay, the 2 yellow and the 1 pink color, and make it into a triangle. Okay, so if you notice this, sorry, hold on now. Okay, if you take a look at this one actually you can bring it down. Oh man. Okay, it will become something like this. Let me rub it off. Okay, so the downward force is this way. Then after that, the rightwards force, what you need to make sure is that the 2 component forces follow one after another. Okay, so if they follow one after another, you will notice that this particular one, okay, will be like this. It has to follow one after another. Okay, and then finally, this last one that is going down and right, okay, is the single force that is resolved. Okay, which is sorry, not resolved, is the resultant forces. So it will be like this. Okay, so the single force that is down, right, the original force, okay, and the triangle, sorry, and the 2 resolved forces make a right angle triangle. Okay, so this will be how you would do this. So label it Fy for the vertical component and Fx for the horizontal component. Likewise, with this one over here is the same, up and right. You know what, I'm too lazy. Okay, um, so we start with the up one first lah. Okay, up, and then after that right. Okay, and then remember the original force is upright. This one. Okay, this one now. This is the original force. So make sure you complete the triangle. Okay, it doesn't have to be very perfect, except that you need to make sure that this is marked as 90 degrees. And then, of course, label the vertical component is Fy, the horizontal component is Fx, and the resultant force, okay, is the F. Okay, that's basically, there are many variations of this lah. Okay, I can also do like that. Okay, right, and then up. But you notice that the resultant force is still the same direction. Okay, these two are still the same direction. So there are many different variations of this triangle. Okay, but the most important thing is that the resultant force must follow the original direction of this force. Okay, then I think you're good to go. So which method is the most suitable to cut grass more efficiently? I think this is a logical question. You don't even have to think so much. Okay, of course, you want to cut grass, right? You have to push the lawnmower downwards lah. Pulling it, yeah lah, can. Pulling it can make the lawnmower move, but pulling it just makes the lawnmower go higher. Okay, which you don't want. We want the lawnmower to be as close to the ground as possible so that the blade over here can cut the grass. If you pull it up, sure, it can move forward, but it's also moving upwards. Okay, and it doesn't help unless you want a shorter grass lah. Okay, fine. If you want short grass, then can. But I think this one is really talking about cutting grass properly. So, of course, the answer is the pushing method. Okay, the pushing method is the most suitable one. Okay, because and then we give the reason for we physics it lah. Okay, the downward force is bigger, or the downward force is greater. I think any one of these is totally fine. Okay, next question. So this is a different story. Okay, so just now we talked about resolution of forces. I give you one resultant force, you split it into two. Now this question is talking about equilibrium of forces. Now if you joined us last Saturday for the MRSM session, okay, I did speak about this, and I said that okay, I'm going to tell you that there is a very main difference because both these subtopics, okay, talk about a triangle, okay, except that both triangles, they look the same, okay, but they are drawn differently. Okay, so I want you to be very aware that equilibrium triangle is not the same as the resultant force triangle. So this is a resultant force resolution of forces triangle. Okay, the one that we're about to see is the equilibrium triangle, okay, which is a different subtopic altogether. So the first question is state the meaning of the equilibrium of forces lah. Okay, so the equilibrium of forces is a situation where all the forces acting on an object have a zero resultant force. Okay, so based on your knowledge of the concept of force, draw the force triangle to show why the durian is still hanging and not falling. Okay, so this is important. Let's consider this one now, okay? Sorry, the three forces that are involved. Number one, you have the original one, the weight. Okay, the weight force is downwards over here. So I'm just going to draw this like this, okay, downwards. Now, the second one is at an angle of 30 degrees, okay, but it's going this way. Okay, and the third one is also at the angle of 30 degrees and it's going that way. Now, the most important thing, okay, and this is where you should take note. The most important thing about the equilibrium triangle is that all these three forces have to be in one direction. And this is what I mean. Look at the resultant force that I showed you just now. There are two forces that are in one direction and then one force is a different direction. Okay, so this is a resultant force graph. But an equilibrium triangle graph, okay, you need to arrange these three forces, okay, in such a way that they form one triangle that is one direction. Okay, they form one triangle that is one direction. So again, the easiest method would be to take the force one by one and then place it so that they follow one whole line lah. Okay, so this first one, I'm going to bring it down. Okay, I'm just going to put it here and we're going to label this as W. Okay, or fine, sure, you can put the W over here lah. Okay, the second force, I'm going to follow the direction. Sorry, not just follow the direction. I'm going to take it and, oh, sorry. Okay, I'm going to take this and just let it continue, okay, from the previous one. And then finally, this third one, okay, we're just going to make it continue. I know it's a bit, yeah, sorry, it's a bit ugly lah. Fine, fine, fine. Okay, but that's the idea. All you have to do is just draw a triangle where all the three directions, okay, are one after another. Okay, and then of course, label your this one properly lah. You have T1, okay, that is upright. Okay, and the second one is T2, okay, that is upright. Okay, now if you notice, okay, so this is the other thing. If you notice that actually if I extend this W up, okay, it is the same, this one, you'll notice that W actually forms a 30-degree angle with both T1 and T2. Okay, so what you can do is you can draw here as 30 degrees and then here is also 30 degrees. Okay, and that makes it a complete triangle. Okay, the most important thing, whenever you draw this triangle, one mark is just for the triangle, the second mark is for the angle. You don't have to label both angles, but you need to be very aware, okay, of what the angle is. At least one angle is written down. Okay, and usually what you can do is just extend this all the way out so that you can see, oh, okay, W dengan T2 bahkan it makes a 30-degree angle. So then you can, you can have this one. So this is a complete answer. Okay, one mark for the triangle and one mark for at least one angle. Okay, that is given over here. Okay, so again, everybody, please notice the difference. Equilibrium triangle, all three forces is one way. If it is a resultant force triangle or resolution of forces, you have two forces that are going one way, which is vertical and horizontal, and then the resultant force goes the other way. Kind of completes the triangle, okay, except that it's going a different way. Okay, or if you want, you can also call it a shortcut. So, if the rope labeled T1 snap, okay, so worst case scenario, you're having a durian and then this T1 just snaps. You're left with T2. Okay, think logically, what's going to happen? Okay, so what happens to the tension labeled T2? Of course, the tension will increase lah. Okay, because the other string that was holding up the durian, okay, is no longer there. So now all the burden is left on this one string alone. So somebody once told me you can replace the word tension, and I don't recommend this. You can, if you don't really understand what is this tension, think of it in terms of the burden. Okay, the burden of the rope. Okay, and since T1 snap already, means all the burden of carrying the durian lies in T2. Okay, because T1 is useless here. So of course, the burden, the tension will increase. So one equation that relates the tension to the rope, okay, if you think about it, sorry, I drew it already over here. Please forgive my ugly durian drawing. So since it is, I guess we have to assume that the durian still hasn't dropped lah. Okay, so it is still in equilibrium. Okay, except now the upwards force is the same as the downwards force. So W equals to T2 is the equation for this thing. Number 3, same thing. Okay, forces in equilibrium, but now our two tensions, our two cables have the same length and the same angle. Whereas the one before this, they had the same angle, but they are different lengths. Okay, this kind of unique. We don't see this kind of question very often, but this question is more common. Okay, we have a picture frame or this thing over there. Now, most important thing is whenever you see this situation, the first force that you must label is the weight force. Okay, if you don't label the weight force, it's very difficult to draw triangle because you need three, this one. Okay, so always remember that there's a weight component involved, okay, in this. So our first question, what is meant by forces in equilibrium? I think we answered this. Okay, all the forces acting on an object have a zero resultant force. So I'm not going to answer this. Okay, once again, the triangle. Remember what I said just now. Triangle must be one way, okay, which if you notice over here is down, down over here, and then up right, and then up left. So you can just first using a ruler, okay? Obviously using a ruler. So down, sorry, downwards force, and then you have the upright force, and then you have the up left force. Okay, just this one. The only thing now is the 55. Okay, just now I said that the W is touching the 30. Okay, because it is. But look at this situation. Okay, this is a very different situation altogether. If I extend this all the way up, you notice, sorry, oh no. Okay, if I extend the weight component up, you notice that the 55 is not touching the W. Okay, and this is important. So if the 55 is not touching the W, what is actually touching the W? What's the balance? If this is 55, here is 90, this will be 35. So the 35 is the one that's touching the W. Okay, so make sure that here you label 35. Of course, the other side is also the same. Okay, and I guess to make the whole thing complete, just 110. If you notice that actually the 110 is 55 plus 55, and that's actually where this component goes. Okay, if I break, and you don't have to draw this, but if I break this into two, this is actually 55, and this is actually 55. That's where the 55 went, okay, in this particular scenario. Okay, the weight of the notice board. Notice board is given as 20 kg. So I think if you calculate the weight, this is pretty easy. Weight equals to mass times gravity. Okay, so it's 20 times 9.81, which will give you 196.2 newtons. Okay, please correct me if I am wrong. Okay, and then the value of the tension in the cable T. Okay, this is where you can use, okay, one of the few moments that you should use the sine rule. Okay, don't make life difficult by resolving the forces, use the sine rule. Okay, if I have 196.2 newtons over here, I can use the sine rule. I just need to find one of these T's. Doesn't matter which T because they are both the same T. Okay, so if we apply the sine rule, since I want to find T, I'm going to put the T on top first. T over, and this angle is 35. So sine 35 equals to, and the complete set I have is 196.2 over sine 110. T over sine 35 equals to 196.2 over sine 110. And if you do the math properly, then you will get T equals to 119.758 newtons. So diagram 4 shows identical springs. Okay, so when we hit the topic of springs, the first thing you need to be aware of is this thing called Hooke's law. Okay, I think you can review in the black book what is Hooke's law. I don't think they're asking this in this set. Okay, but just know that when we talk about springs, we're talking about Hooke's law. Okay, a couple of things will apply. We're going to talk about this in a while. Okay, secondly, the spring constant. Okay, when you see the word spring constant is a representation of what we call the stiffness of the spring. Okay, so a bigger spring constant means that the spring is much more stiff lah. Okay, dia lebih, I think in Malay it's called keras lah. Okay, I can't remember. But it's called, it's a stiff spring lah. Okay, so an example would be like the motorcycle punya, that thing, the spring on the motorbike. What is called suspension. Okay, the suspension spring is a very good example of a very stiff spring, which is good lah. You know, you don't want to go on the road and then kamu goncang-goncang begini kan, terus the motorcycles will go up and down. It's not a good idea. That's a very lousy spring lah. Okay, unless you're the kind of person that likes to do this kind of antics on the road, which I'm like, okay, what a waste of life. So a very non-stiff spring is, for example, like if you have the spring pen, the tick on, right? It's a very, very lembut in spring. Okay, so a non-stiff spring will have a smaller spring constant, a stiffer spring will have a big spring constant. Okay, but I like this first question and I insist that you start this question. What is meant by this spring constant 20? It is not asking you about what the stiffness of the spring is. Rather, it says that um, the spring will require 20 newtons, okay, of force or weight, okay, or force lah, okay, to compress or extend it by 1 cm. Okay, I love this question because it's very, very rarely asked. Okay, so I think it's, but that's what this means, 20 newtons per centimeter. So if you logically think about it, if it's 20 newtons per centimeter, means if I want to compress it, or if I want to extend it 2 centimeters, I need 40 newtons. That's what this number means. Okay, 20 newtons per centimeter. Except that I want you to pay attention that this particular unit is centimeter. There are 2 units for spring constant. The most commonly used one is Newton meter. So how can the spring prevent the baby from strong shakes when the baby stroller moves on a rough surface? Okay, so the spring over here is kind of like a suspension spring now. Okay, now most, I think if you understand how the springs work, okay, when it moves on a rough surface, okay, the spring, okay, will extend and compress. Okay, when it moves on a rough surface. Okay, so as it moves, the stroller is going up and down, so the spring will extend, compress lah. Okay, I think that's logical. The second one, and this is the one I think is very crucial because we cannot use the words very interchangeably. Okay, what actually happens is that the spring absorbs the energy, okay, from this movement. Okay, the constant extending and compressing will cause the spring to absorb the energy. Okay, the wrong answer is to say that the spring will absorb the force. Okay, I think that is really not it's really not acceptable lah. Okay, what actually changes is the amount of energy, which then this translates into a much smoother experience for the baby lah. Okay, so please take note, the word absorb force is rejected in this particular question. Okay, next question. If the weight of the baby is 80 newtons, calculate the compression of the spring. So, first of all, since you're given the force, Hooke's basic law, the formula is F equals to Kx. Okay, where F is the force and K is the spring constant. Okay, and so I think it's pretty simple. 80 equals to your K is given, K is given as 20. Okay, 20, and then you can calculate the X lah. Okay, so you do this, you get X equals to 4 cm. Okay, what you need to be careful of is the fact that I wrote 4 cm instead of 4 meters. Why? Because our K, why do I keep using pink color? Because our K is Newton per cm, okay, and not Newton meter. So be very, very careful about this. But actually, what is more important, okay, is the second question, the elastic potential energy of the spring. This one, die also, you must use meters. All forms of energy, okay, the unit for potential energy is joule. And because we are using joule, you must use the extension or the compression in meters and not in centimeters. Okay, formula for elastic potential energy, there's two. E equals to half Fx or E equals to half kx squared. Really depends on what you want to use. I think if you use either method, it's fine. Okay, except that please don't forget the x, okay, the extension must be in meters. Okay, so if I use half, our force is 80. No, force is what? 80, yeah. Force is 80. Our extension is 0.04. Sorry, let me backtrack first. I think it's the way the question is worded. So I thought that it's talking about the total compression of all the four springs, but actually it's talking about that one spring. Okay, first of all, notice that this arrangement, okay, this arrangement of springs is what we call a parallel arrangement. Okay, so we assume that all four at one go lah. So this X over here refers to the total extension. Okay, the total compression. The total compression of the springs is 4 cm. Okay, so if you divide it equally by 4, okay, so the compression of one spring, okay, is 4 cm divided by 4 springs, which will give you 1 cm. That's why there's a third mark over here. By the way, the takeaway from this, okay, is the formula, okay, and the fact that make sure that you calculate the x in meters. Okay, number 5, let's move on. So diagram 5.2, question number 5 is, if you take a look at question number 5 is a compare contrast. I think we did discuss this, but we're just going to do this anyway. So first, state the meaning of elasticity. So elasticity is a property. Okay, it's a property of material. Okay, that enables an object to return to, the keyword is its original shape and size after a force applied on it is removed. Okay, keywords being property, object return to its original shape and size after a force, okay, is removed. Keywords are this. Okay, so the number of springs, this is a compare question, okay. So if you look at the number of springs, I think it's quite easily see 5.1 is less than 5.2. Okay, I don't think this is a very big deal. Okay, the compression of the spring, if you take a look, this girl is lower than this girl, which means that they are more compressed. Obviously, the starting point is the same, okay, but since she's going lower on 5.1, okay, that means she's compressing more. So the compression, okay, will be 5.1 is bigger than 5.2. The spring constant for the spring system. Remember, the word spring constant refers to the stiffness. If it is very stiff, then it's very hard to compress. Okay, because, it's keras lah. So the spring constant, I wonder whether it's given. Oh, it's not given. So you have to understand this. Okay, so the spring constant in this particular case, okay, will be 5.1 is smaller than 5.2 because it's harder to compress 5.2. Okay, that's why the stiffness is bigger. So remember, spring constant is a representation of the stiffness of the spring. I think if you understand this, it's pretty easy to understand spring constant. Okay, so state the relationship between number of springs and compression. Number of springs is less, compression is more. So one bigger, one smaller. Okay, I think for the sake of time, and because we've done this so often that you can write your own long-worded answer. Okay, I'm just going to give the short version. So the bigger the number of springs, the smaller the compression of spring. Okay, in the exam, please write full sentence. We're just discussing this as an exercise. So yeah, let's take away this. Okay, compression and spring constant. If you take a look at these two, both are also opposite directions. So, and this is important. The spring constant is the one that determines the compression. The stiffer the spring, okay, the smaller the compression lah. Okay, it's not the other way around. I know that in this question they put the words compression first and then spring constant, but think about it. Spring constant is an inherent property of the spring. Okay, it belongs to the spring. It's not something that you can change. Compression is something you can change. So because spring constant is the manipulated variable, we always put the spring constant first. This one I'm going to write the full answer. Okay, the bigger the spring constant, the smaller the compression of spring. A little side note that I wrote as I was reviewing this paper, I think it's good for us to remember this. So K is a spring constant lah. So when we talk about series and parallel arrangement, so in this particular diagram that you see over here is parallel arrangement because the springs are one after another. A series arrangement is if you have one spring followed by another spring and followed by another spring. So this is a series arrangement. This is a parallel arrangement. Okay, very much same like the resistor punya arrangement lah. So a series arrangement and a parallel arrangement, they affect the spring constant very differently. Okay, so this is what I mean by this. Okay, if you want it to be less stiff, which is, you want a softer spring system, okay, you either need to have more springs in series. That means the more springs in series you have, the less stiff it will be, or a less springs in parallel. Like this situation, okay, this one is less springs in parallel. So the spring constant is less. Okay, so a very good example of this more series, okay, is a bungee jumping rope. Okay, bungee jumping rope is basically one spring after another and arranged in such a way, okay, that it can extend as far as possible before breaking. Okay, I'm sorry, did I say breaking? I'm not breaking lah. Before, so they can extend as far as possible without breaking, not before breaking, without breaking. Okay, and because of it, it's less stiff because it's so extendable. Okay, on the flip side, okay, on the other side, if you want a stiffer spring system, have less springs in series or more in parallel. Okay, a very good example of more in parallel is mattress, a spring mattress. Okay, and I am very aware that when I say the word spring mattress, I'm referring to a lot of old technology because I don't know who sleeps on spring mattress nowadays, but spring mattresses are fun to bounce on now. Okay, and so spring mattress are all these, mattresses. Sorry, it's like, wow, one spring, 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 like that. Okay, so all these springs they are arranged in parallel, so it makes the bed very stiff. Okay, of course you can still bounce on the bed lah, sure. Okay, but it makes the this one very stiff, so it doesn't like wow menjadi sangat 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 like soft lah. Okay, so I hope these notes help lah. Okay. D, the spring system in diagram 5.1 experiences a compression of 6 centimeters. Okay, take note of this. When a girl weighing 250 newtons sits on it. Okay, given that the weight of the horse is 160 newton, determine the constant string. Okay, so first, 5.1. Okay, 5.1 is 2 springs. Okay, so if you have 2 springs, okay, like this, and the compression is 6 cm. The spring constant, okay, so we have F equals to Kx, okay, and our total weight is 250 plus 160. Okay, so 250 plus 160, okay, equals to K, and then the compression is only 6 cm. So since the total compression is already given, there's actually no need to times 2 because you're already considering the entire system itself. Okay, but the thing is, change the 6 cm to 0.06. Remember, always use meters. Okay, and then you will get K equals to 6 833.3333 Newton per meter. Okay. Spring in diagram 5.1 is replaced with a thicker spring. What happens to the compression of the spring? A thicker spring usually results in a softer spring. So a softer spring means the compression will, sorry, a thicker spring. Did I say softer? A thicker spring usually means that it is a stiffer spring. If the spring is stiffer, the compression decreases. Okay, and this is a good time to talk about the factors that affect the spring constant. Okay, apart from the material itself, the three main factors are the thickness of the spring, okay, the length of the spring, and the diameter. Okay, the diameter of coil. Okay, so when we talk about thickness, the bigger thickness, okay, a bigger spring constant lah. Okay, in terms of the length, a bigger length, if you have a longer spring, okay, the spring constant becomes less. It becomes less stiff because the spring is very long, okay, as opposed to a shorter spring. Finally, the diameter of the coil, a bigger diameter, okay, results in a bigger spring constant. So if you have a spring that is this tiny and a spring that is this big, okay, a much bigger diameter of the coil, okay, results in a bigger spring constant. So good notes to have, at your side when you're reviewing this paper. Okay, again, you see question 5. Diagram 5.1, 5.2 show picture frames hung on a wall with identical strings. Okay, so you have two ways of, hanging up a picture lah. Now, there's this important piece of information. Each string can withstand a maximum force of 16 newtons. Okay, let's just keep it at the back first, okay, while we answer this. So, meaning of forces in equilibrium, we've already covered this, so I'm not going to go into this. Compare the angle between the string and the picture frame. Okay, looking at the angle, one is 40, one is 60. I think this is pretty easy. Okay, the angle, punya lah panjang. Okay, angle between the string and the picture frame. Okay, in this particular case, 5.1 has a smaller angle than 5.2. Okay, next, the weight of the picture frame. The weight is given. Okay, so I think it's a very easy compare. 5.1 is bigger than 5.2. Okay, and the tension also given. This is amazing. Okay, the tension is given. 5.1 is 5.1 is bigger than 5.2. Okay, so I think it's an easy compare lah. Okay, you shouldn't be getting this wrong. Okay, relate the angle and the tension. So if you take a look at the angle is less. Okay, the direction of the angle is less and the tension is more. So one less, one more means the bigger, the smaller. Okay, so again, I'm just going to use arrows. The bigger the angle, the smaller the tension. Okay, because this is pretty straightforward. The angle determines the tension, not the other way around. Okay, the weight of the picture frame and the tension. Also the same, the weight determines the tension. Okay, but if you take a look, both of them are in the same direction. So the bigger, the bigger. Okay, the bigger the weight, the bigger the tension. I think this is difficult lah. This one can. Okay, all right. The picture frame in diagram 5.1 is replaced with a new picture frame. Okay, a few seconds after the frame is hung, it is found that the string of the picture frame snapped. Wow. Okay, if the weight of the new picture frame is 25 newtons, okay, so now you have a different weight. Okay, but it is, everything else is the same. So this is where you need to draw the triangle of equilibrium of forces. Okay, so when you draw the diagram of equilibrium of forces, you find that the 40 degrees and everything, okay, makes up the 80 degrees at the center. Okay, because, okay, let me draw again. The weight is down here, right? Okay, so it's touching this one. The T1, the tension is touching the weight at this angle, which is 50 degrees. So when I redraw the triangle, the weight and the tension, okay, make an angle of 50 degrees. On one side is 50, on the other side is 50, so the balance is 80. So in order to calculate the new tension of the string, I just want to find T lah. Okay, same lah, we use again the sine rule. So T over sine 50 equals to W, which is 25 newtons now, over sine 80. Okay, you calculate this, you get T equals to 19.447 newtons. So the reason why the string of the picture frame snaps is because of this statement that the question made earlier. Each string can only withstand a maximum force of 16 newtons. Okay, the maximum tension is 16 newtons. Okay, but you find that our new tension now is 19.447. Okay, so that's why the string of the picture frame snaps now. Okay, because the tension of the string is bigger than the maximum force. Okay, which is 16 newtons. Okay, the new tension of the string that we just calculated. Okay, next question. Diagram 5.1 shows two springs with the same original length. Okay, then after that, you put a 10 Newton load. Okay, right from the get-go, you notice that the weight is the same, but the extension is different. Okay, the one in 5.2 extends more. Extends more means that it is a less stiff spring. Okay, one look at the diagram and you must be able to tell me this. The weight is the same. Okay, for example, I hang the same baby on both springs, but spring B seems to extend more. Okay, and the main reason is because it is less stiff, therefore spring constant is less. Okay, elasticity, I think we covered this 2 questions ago, if I'm not mistaken. Okay, elasticity is yada 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 yada. So I'm not going to write it here. Okay, next. What is the type of energy stored in the springs? All springs store elastic potential energy. Okay. Compare the diameter of spring A and spring B. I think I would say the diameter is the same. Wait, does it tell me to? Yeah. Okay, the diameter is the same. Unless my eyes fail me, it looks the same to me. That's pretty strange. Okay, the extension of spring A and spring B when attached with 100-gram loads. Okay, this one I think is easy to see. In terms of the extension, B has a bigger extension. Oh, sorry, let's start with A. So A is lesser than B. Okay, and in terms of the spring constant, since spring B extends more, okay, we have to, conclude that A has a bigger spring constant than B. Okay, because the extension is less. So based on this, the relationship between extension and spring, same thing. Remember everybody, spring constant is a manipulated variable. It's an unchanging value. So the relationship that you write must start with the spring constant, not the extension. Okay, so the bigger the spring constant, the smaller, okay, the extension. Okay, the bigger the spring constant, the smaller the extension. And this is Hooke's law lah. Okay, please pay special attention to how Hooke's name is written, H-O-O-K-E, Okay, these are the kind of things where people tend to lose marks because they just simply write people's names. It's HOOKE. Okay, please remember this. Okay, original length for spring B is 8 cm. Calculate the spring constant if the length in diagram 5.2 is 12. So the first thing you need to count is the extension. The extension is 12 minus 8, which is 4 cm. Okay, you are given a force of 10 newtons. So F equals to kx. I'm going to change the x to 0.04 meters, okay, just to be consistent with this. So 10 equals to k times 0.04, which will give me k equals to 2,250 Newton per meter. So we now come to the set of questions where they're asking more on making the choice, question 7 or question 8, and also the modification. Again, there's no essay questions in this set. I think we're pretty much okay lah. All right, the food delivery man with a mass of 70 kg cycling a bicycle and given the acceleration. Okay, take note. What is the meaning of acceleration? Acceleration is the rate of change of velocity. Okay, not a very good idea to put the formula as a definition. Okay, so as much as possible, try to remember the definitions. But if you really don't know and if you really cannot remember, you can try to put the formula, but the chances are very slim now, okay, that they will allow this answer. The only definition that I know that involves a formula is the momentum, this one, P equals to mv. Even then, you have to write P is momentum, M is mass, V is velocity, in order for you to get the full mark, the full 1 mark, okay, for the definition of momentum. Otherwise, if you remember, momentum is the product of mass and velocity. It is so much easier, product of mass and velocity. It's just 5 words. Daripada kamu menulis yang begini, bahkan yang is really not worth 1 mark. Okay, you have to write what's P, what's M, what's V. So please try to remember this. Okay, if the mass of a bicycle is 12 kilograms, okay, and the mass of the item being carried is 5 kilograms, and then don't forget the guy's mass is 70 kilograms. So what is the force, okay, that is needed? So of course, when we talk about this, we go back to the first forces and motion one, which is force equals to mass times acceleration. We need to calculate the total mass first lah. We are given the acceleration. Okay, so make sure you know how to substitute. The total mass is 70 plus 12 plus 5. 5 kgs of item. Wow. Okay, so force is this one multiplied by 0.3. Okay, you will get about 26.10, and all forces are all forces are newtons. Okay, so you can't really run far from that. So why is this 3 marks? Because the addition of the forces is 1 mark, substitution of acceleration is 1 mark, final answer with the unit is 1 mark. Okay, so even in Form 5, Chapter 1, you cannot run away from this one because F is always about the resultant force. Okay, Table 3 shows the set of bicycle frame, material tires, and storage box densities that can be used by the food delivery man. I think this is a very, very easy question. Okay, you shouldn't fumble on this. Given the choice between iron and titanium, of course, you would choose titanium. Okay, the main reason is because iron, if you know your chemistry, iron is ferrum, and ferrum rusts very easily. Okay, so titanium does not rust easily. Okay, you can also say it has a lower density. Okay, because lower density can make the delivery faster. Okay, so it's lighter, I can move faster, you can accelerate faster. Now, of the 2 answers, I would prefer if you give lower density, okay, because does not rust easily, although it is correct, okay, it has very little relevance to the kehendak soalan. Because the question is asking for you wanted to make delivery faster. So what if the bicycle rusts easily? Okay, as long as it can perform. Okay, so but I think it's a good thing to know that, okay, if you're going to answer titanium, one of the possible answers is does not rust easily. Okay, but just to be clear, I think the preferred answer is lower density because it answers the question. Okay, so make sure you know the difference. Okay, when you answer a question, don't just answer because you remember that this is the answer, but make sure that the answer has relevance to what the question wants. The density of the storage box also the same. Obviously, you want a lower density lah. Okay, you don't want ferrum, you don't want a high density because high density means very heavy. Very heavy means you're already carrying 5 kg of stuff, Then if you put the storage box so heavy, it's like even worse. So lower density or smaller density, okay. And generally the answer for lower density is less mass. Or you can also answer to increase the acceleration, which is another fancy way of saying to make the delivery faster. Okay, it's just a fancy physics way to answer this lah. Okay, I think increased acceleration is also good. Okay, because lower density of storage box lah. So any one of these two answers is fine. The best set obviously is set H lah. I don't think this is a very big issue. I think it's a pretty easy question. Okay, next. Diagram 7 shows a car of mass 1460 kg pushed by a man with a certain value of force on a rough surface of the road. Okay, this is an important statement. I don't know whether it's got relevance to the question later, but whenever you see a rough surface, means there is frictional force. Okay, if there's no rough surface, the opposite of rough surface is a smooth surface. Okay, if you see the words smooth surface, it means that there is no frictional force. Okay, so what this means is that this poor guy is pushing the car with all his might, and at the same time, there's a frictional force that is working against him. Okay, that is so annoying. There, name the force that opposes the motion of the car. It's called the frictional force. Okay, and you know it's there because the question says rough surface of the road. Okay, show the direction of the force, already shown. Okay, as long as you show that it's going opposite to where this guy is pushing. Guy is pushing forward, car is moving forward, frictional force always opposes the motion of the car. Now, if the net force exerted on the car is 420 newtons, and this is a good thing because we don't know any of the forces, but what this word net force means, okay, is that the force forward, okay, the force forward minus the force, the frictional force, okay, is 420 newtons. Okay, and so you can actually just straight away put it into the F equals to MA. 420 equals to the mass of the car is 1460 with an acceleration. But actually, Emerson, the acceleration is so pathetic. Okay, 0.2877 meters per second. Oh, sorry, per 28 centimeters per second squared. Okay. Table 1 shows the different characteristics of the load. Density of the material of the car body is given over there. Battery capacity is there. Okay, so usually what do we want? Oh no, the English is not there. I suppose kereta dapat bergerak dengan lebih cepat lah kan. I think that's the general this one. So the car can move faster. So again, like the question just now, lower density. Okay, and we pretty much can use the same answer as before. Lower density means less mass, which means that you can increase the acceleration. Okay, at this stage, we are probably going to go with P because P has the lowest density. Okay, so you want a battery capacity that is high. Actually, I know 100 is higher, but it's not that far from 95. Okay, so a higher battery capacity, okay, is good because a higher battery capacity means you have higher power or more energy. Okay, to play your radio lah, to turn on the electronic systems in your car or whatever. Okay, so the electric car that you want is electric car P lah. Okay, for all these reasons. So you kind of see the pattern over here. If the question is talking about moving faster, Okay, sorry, I don't know what this full question is because even if my digital version it shows this, so I just assume that kereta dapat bergerak dengan lebih cepat lah. Okay, the car can move faster. Okay, so just to remind you, okay, which is an important thing, make sure that the stuff in the question does not appear in your answer. Okay, make sure it does not appear in your answer. Okay, so you have to write it in different ways. Okay, in this particular case, writing it as increased acceleration, I think is easier lah. All right, Malacca, we're slowly coming towards the end. So this is an archery, okay, archery situation. If we have archery situation and you're talking about extension, you know that this is about Hooke's law. So we are coming back to Hooke's law again. Okay, so the bowstring and the bow is over there. And there's an extension of X that you see. So when the arrow is released, it will travel at the speed due to the elasticity of the bow. So what is the physics law that's related? Obviously is Hooke's law. Reminding you once again that the spelling of the word hook is very important. Okay, so the force applied by the archer is 200 newtons. Spring constant is 3. Notice this is per centimeter. 200 equals to the, oh, okay, times X. Okay, I think this is a good time to talk about this. Because the Malay says is 6. Sorry, I was looking at the 6 just now. So the X is 33.3333 cm. Okay, so let's settle this once again. Let me stop it, Emerson. Okay, let's settle this. What happens in this situation? Okay, I think just stay true to the question that you were given. If you originally answered in English, just follow everything in English. Okay, the examiners are not so cruel. Like, okay, we'll only accept the answers that are answered in PM. No lah. Okay, it's not fair because you read the question in English. Okay, and just so happens that the spring constant for both in Malay and English is different. Okay, I think if you use Malay, you should answer the 33.333. If you answer in English, then I think getting the answer 66.6667, okay, is really not an issue lah. Okay, just don't get hung up by this. Okay, diagram 8.2 shows the most important component of a vehicle suspension system. Wow. The spring. Okay, state the modifications on the spring to further improve the suspension system of the vehicle to make it move steadily. I think the same question as the pram just now. So the length of the spring should be a bigger length. Okay, so that the spring constant is smaller. Small. Okay, or it is less elastic. And this is a good thing because this is a vehicle. I don't know what vehicle this is. I'm going to assume it's a car. You don't want it to be too stiff, okay? Especially in an uneven road. It needs to bump up and down. Sure, it makes people uncomfortable, okay, moving up and down. But actually, the constant moving up and down actually is less stress on the body as opposed to if you have a very stiff spring, okay, and then, you're just basically shaking is not a good idea. Okay, so a smaller spring constant, I think, is the way to go for this. So because of that, you need to have a bigger length. The diameter of the spring wire should be small. Okay, for the very same reason. Okay, smaller spring constant. Yeah, okay, or less elastic. Yeah. The diameter of the spring wire, the thickness of the spring. Remember, this refers to the same thing as the thickness, okay, or the cross-sectional area. All this is talking about the same thing, okay? The diameter of the spring wire, the thickness of the wire, the cross-sectional area of the wire, okay? It comes in these three most common ways of asking this. It's not asking about the thickness of the spring, but rather the wire itself, whether it's a thick wire or thin wire, okay? Next, the type of material. Okay, usually we will use steel, okay, or I guess you can use titanium, or you can also just say a strong kind of material. Okay, if you're going, you know what? Let me change the color. If you're going to say steel, okay, if you're going to say steel, then the answer can be stronger, okay, or last longer. If you're going to say strong material, okay, then I would say the reason will be more durable, okay, or even last longer, okay, also can withstand a bigger force, okay. All this, actually, even steel also can use all the answers in blue, lah. Okay, but I'm just saying that you shouldn't put the answer, the type of material is strong, and then the reason is stronger. Cannot, this one cannot. Okay, so just make sure that you don't write stronger twice. Okay, so stronger, lasts longer, durable, can withstand a bigger force. All these are good things. Okay, for car, for vehicle suspension system. Number 8. 8.1 shows a graph of this. Okay, I think we covered the meaning of elasticity. No, adamantium doesn't exist. Okay, still the meaning of elasticity. I think we've covered this. Calculate the elastic potential energy. Okay, for spring P. So we're only interested in this graph. Okay, the F is 18 and the X, okay, the good news is already in meters, so it's really nothing much to this. E equals to half Fx. Okay, so half times 18 times 0.04 will give you 0.36 joules. Okay, always double check. Remember, always double check to make sure that your extension is in meters and not in centimeters. I think this is a pretty easy question. Also, I think we should make notes about this lah, okay? Because this is a common graph. So this graph, okay, shows you two very important things. Number one, F against X. Okay, the F against X graph, okay, the gradient, okay, represents the spring constant. The gradient represents the spring constant. The second piece of information is actually this triangle, okay, which we call the area under the graph. So the area under the graph represents this thing called the elastic potential energy, which if you consider, we actually just literally calculated this. What is the area under the graph? The area of a triangle is half base times height. What is our base? Our base is the extension 0.4 over here. What is our height? Our height is the force. Okay, so if you consider this is actually half, our base is the X, our height is the F, which is actually the formula for elastic potential energy. Okay, so yeah, good thing to know. I mean, these are things that you should know lah, okay, about an F against X graph in this particular case. There are two pieces of information, gradient, area, and then graph. Okay, C. Diagram 8.2 shows a cradle used to put a baby to sleep, which is kind of what I need now. Hold on. To sleep. Okay, so state the characteristics of the spring that is suitable for accommodating a larger baby. What larger baby like me? Okay, so that is safe and easier based on the following aspects. Okay, number of springs. Obviously, you want to have more number of springs because the more number of springs you have, the better lah. Okay, more number of springs. Okay, because the more springs you have, it is. Oh, okay, fine. More number of springs usually means that it is stronger. Stronger usually also means a bigger spring constant. Okay, or bigger stiffness. Okay, and then of course, when we talk about this, the spring arrangement, okay, it should be parallel. Okay, because we want to rock the baby to sleep. We don't want to scare the baby by putting it in series, then forcing the baby, no matter how large the baby is, scaring the baby into bungee jumping. So that's what we don't want. Okay, so a parallel arrangement, probably the same reasons as before: higher spring constant, bigger stiffness, okay, and so on and so forth. Lah. I believe we're at the last page. Okay, so the last one is spring constant is high spring constant. Wow. Okay, higher spring constant always usually means bigger stiffness. Okay. Another alternative answer will be less extension. Okay, lower extension. And this is good because you just want to extend a little bit, not extend like this. Okay, yang bikin itu baby, instead of sleeping, the baby will be laughing. Okay, so it's not a good idea. You want a lower extension, okay, in order for this to be good. Okay, I think that's about it for today. I think if you notice the pattern in this series that we've been doing, uh, it seems to be gravitating more towards Hooke's law, but there are also some questions with forces and equilibrium. There are a couple of things that I didn't mention because it's not covered in the questions. Okay, so I think if you want to know more, of course, you have to read up more. But I think as a basic, okay, depending on where you are with your physics, I think the basic stuff that you need to know about this chapter is already covered. Okay, so before we call it a night, uh, once again we have the words of wisdom. Recently, I bought a book. I bought a book that's pretty interesting. It's called Just Remember. It's a series. It's a collection of poems that I thought that I want to share with you as our motivational quote of the night. Okay, just remember, you're not the first to feel nervous. You're not the first to feel heartbroken. You're not the first for anything. And as unique as your experience may seem, there is someone out there who understands. It's what makes this world feel a little less lonely. The end.